So let's try this again. A little technical difficulties there. Folks, listen up. This is important. If there's one thing I want you to realize, it's this. If you're moving in a circle, we're going to start out with winner minus loser, but it's going to be winner minus loser equals FC, F circular. And F circular is mass times circular acceleration. It's either going to be mass times v squared over r, or it's going to be mass times the other one, 4 pi squared r over t squared. If you're moving in a circle, your net force is Fc. What that means is circular force, Fc, never appears on your free body diagram, because you may remember when we did forces and we did winner minus loser, the right-hand side, the F net, that number never actually showed up on our free body diagram. It was the vector component sum of everything that was on the diagram. So let's follow along. Imagine you're in a car turning a corner. What's the direction of your acceleration, and what's the direction of the force that acts on you? Hopefully after last day's lesson now, we can answer this. We would say, if you're turning a corner, what path are you tracing out? What shape begins with the letter C? Okay, louder? A circle. If you're traveling in a circle, always, what direction is your acceleration? What did we say last day? No, we absolutely said it was not outwards. We said people think it's outwards because they feel like they're getting pushed out. They're not. That's your inertial mass wanting you to keep going in a straight line. What direction are you accelerating if you're moving in a circle? Always. This is key. This is fundamental. Huh? Inwards. 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 Your acceleration is inwards. It's inwards. It's not outwards. It's not outwards. You see, if you have that, then the second part of this question is obvious. What direction is your net force? Well, force is what times what? Force is what times what since Physics 11? Mass times acceleration. Is mass a scalar or a vector? Scalar. So where does force get its direction from? The acceleration. So if the acceleration is inwards, which way is your net force? Inwards. Yes, no, yes, no. What's the correct answer? A. When you're moving in a circle, your net acceleration is inwards, therefore your net force is inwards. That was that big rant. Remember we subtracted two vectors last day and we found actually it is pointing inwards. It says explain your answer using relevant principles of physics. We just did. In Latin, the word centripetal means towards, pedal, the center, centri, towards the center, center seeking. So when an object is moving in circular motion, it has an inwards acceleration. And because you have an acceleration, that means there must be an unbalanced force in the same direction as the acceleration. So an object moving in a circle has a centripetal net force. Some like to use the following notation. I use the following notation. AC is circular acceleration. It's actually centripetal acceleration, but most of you will think of circle with the letter C. It's easier to remember. FC stands for inwards net force. So here's what that means. FC equals MAC. Mass times circular acceleration. Oh, and we learned two equations for circular acceleration last day. One equation for circular acceleration was that, v squared over r. Or another equation for circular acceleration was 4 pi squared r over t squared. Now, Vlad, these are the two equations on your formula sheet. This equation is not. In fact, the most common mistake kids make is when they're doing this, they're so proud of getting the free body diagram right. They're so proud of getting everything in place. They forget to multiply the acceleration by the mass because these are complicated equations. They forget there has to be an m in front if you're talking about a force. So we're going to make a little note down here. Fc, it either equals mv squared over r, or Fc equals m4 pi squared r over t squared. How do I know which one to use, Mr. Duick? It really depends on what information they give you in the question. If they give you the speed, use the first one. If they tell you how long it took to go around once, the period, use the second one. A chemi handy note. In our winner minus loser approach, the centripetal force will always be the net force. What does that mean? That means it will never actually appear on a free body diagram. One of the common mistakes, kids want to put Fc on the free body diagram because they think it's a brand new force and it should be there. No, it's your net combined force. If you're moving in a circle, if you add up all the forces, I'm telling you the answer is Fc. Don't put it on your free body. Let's try some. A car is approaching a circular turn that has a radius of 60 meters. The coefficient of friction between the car and the pavement is 0.45. What is the maximum speed that the car can safely travel through the turn? This is a job for a free body diagram. I'm going to do top view and then leave a space, and I'm going to do side view because we're getting a little three-dimensional-ish here. Okay. We're zooming in. Here's the car traveling in its circular turn. Now I drew a complete circle, and I know no turns are complete. Make it a roundabout. What path is this car tracing out? A circle. Where must my net force be then? What direction? There has to be a force inwards if that's my car right there. Now you'll notice, Nico, I did not put a C on there. The centripetal force is not what's pushing the car inwards. You know what force is pushing the car inwards? And I'll give you a hint. This is why it's tough to corner in the ice. What? Friction. That's the force that appears on my free body diagram. If you look at it from the front view or the side view, we would say, there's a car tire, there's a car tire, there's the car headlights if we're staring straight at it. Here's the axis of rotation. It's going around a corner this way. We would say there's only one force pushing it towards the middle, friction. Friction. Now, let's continue with this side view picture. What are the forces acting on this car? Get the obvious one. I heard it. Is the car sinking into the ground like quicksand? Is the car lifting into the air like Superman? There must be another force in the opposite direction. What's that one? Okay. That bottom diagram is really my free body diagram. There are three forces acting on this car. Gravity, a normal force, and friction. What path is this car tracing out? A circle. Who's winning? Well, the only place I have an unbalanced force is horizontally with the friction. I'm going to go winner minus loser, but there is no loser this time. It's going to be just winner. It's going to be winner equals, and normally I would say it's the net force. What path are we tracing out? Winner equals circular force. That's the difference. That's the new step when we're moving in a circle. Friction is what times what? circular force is m times circular acceleration. Which equation am I going to use for circular acceleration? It depends. What are they asking me to find? Speed? You know what? I probably want to use the equation for circular acceleration that has a speed in it. Okay, my next line. Mu, oh, I don't know the normal force. Oh, but look. I know another force the same size as the normal force. What? And this equals mv squared over r. Why v squared over r? Because they said they wanted speed. They could have asked how long to go around once, then I would have used the 4 pi squared r over t squared, period. Oh, hey, what do you notice? Do they have different roads for big semi-trucks and for small cars, or can both of them handle the same corners, as it turns out? Now, it's a little bit different because we're assuming the center of mass is on the ground, and for a semi-truck, the center of mass is higher up, which does mean they have to be a little more careful when they corner. But certainly, if you have two cars that are the same shape with different masses, they're fine. Masses cancel. In fact, I think we end up with this. V equals mu g r square rooted. Yeah? This is how they calculate the speed on the road signs. So when you see a road sign and they've got a lower speed on a particular corner, okay, they lower it a bit more, and it all depends. We're not looking at, we're assuming the road is level. Banked corners, you can go a little faster. Mu was what? 0.45. G is 9.8. Radius is 60. $16.3. Or if I multiply by 3.6, you know what? You could do this corner at 60 kilometers an hour. Actually, no. 60, you'd start to slide. You could certainly do this at 50 kilometers an hour. If you went 60, you'd start to slide on the pavement outwards because your inertia would be wanting you to keep going in a straight line. Okay. A test tube rotates with a period of 9.9 times 10 to the negative 4 seconds. What is the centripetal force on a 1.8 times 10 to the 9th kilogram amoeba at the bottom of the test tube? The bottom of the test tube rotates in a circle with radius 0.150 meters. What are they asking me to find here? Show. Okay. And that's always going to be mass times AC. It just depends which AC they want, which equation for acceleration. Look at the information that they've given me here. Have they given me the speed or have they given me the period? How long to go around once? So I'm going to use m4 pi squared r over t squared. Don't forget the mass, because it's a force. Mass times acceleration. We have an amoeba that weighs 1.8 times 10 to the negative 9 times 4 times pi squared times the radius is 0.15, all divided by period squared, 9.9 times 10 to the negative 4 squared. This is the unit where you really want to practice typing this stuff into your calculator. Specifically, you want to know how, if your calculator can even handle a pi squared. Some of you might have to type pi times pi. Some of your calculators won't like a squared after a pi. And practice squaring scientific notation. Oh yeah, you also want to find where your pi button is. You'll be using it lots. You get 0.0187. How about 1.09 times 10 to the negative 2? Is that right? Did you get 0.01? Am I wrong? I'm not hearing any confirmation. 1.8 times 10 to the negative 9 times 4 times pi squared times 0.15 divided by 9.9 times 10 to the negative 4 squared. I think I'm right. Am I not? Yeah. Oh, okay. Turn the page. Try it. Try just going pi squared and hit enter. Yep. That's right. Right. So double check how you're typing it in. If you're squaring it, put the scientific notation in brackets with the squared outside the brackets. Example 3. An empty swing on an amusement park ride has a mass of 10 kilograms. This is the, is it called the Wave Rider at Playland? No.
Crazy Beach Party?
No. The one right next to it, though. The swings, right? The nice tame ride, you go in a circle. Okay. The swing has a kinetic energy of 460 joules. What's the centripetal force on the swing? What do they want me to find here? Okay. Which equation am I going to use for circular acceleration? Psst. Hello, folks. Which equation am I going to use for circular acceleration? Well, they didn't give me a speed, and they didn't give me a period. Oh, what did they give me? Kinetic energy. If I know the kinetic energy, what can I figure out? Oh, I can figure out the speed. Okay, you know what? I'm going to go over here and I'm going to say they told me that the kinetic energy was equal to 460. That means a half mv squared is equal to 460. That means that v squared is equal to 460 times 2 divided by the mass. 460 times 2 divided by 10. Sorry? What'd you get? 92? That's v squared. Although, hey, wait a minute. I was going to square root this, but then I said, wait. What's the equation for circular acceleration that has a v, that has a speed in it? V squared over r. So I could square root that v, except isn't there actually a v squared in my equation? Then why don't I just put a 92 in for the v squared and save myself square rooting it? This is going to be 10 times 92 divided by, where's the, oh, they gave me the radius in the diagram, 7. What do you get? What is the centripetal force on the swing? How many newtons? $131.4? 131? Newtons. Turn the page. Let's see, how far are we going to get here? Yeah, we'll do one more. Okay. A 1,450 kilogram car can travel without slipping at a maximum speed of 32 meters per second in a circular path, moving in a circle, of radius 72 meters on a dry horizontal surface. When it rains, the coefficient of friction is reduced to 1/2 of its original value. What's the maximum safe speed under this wet condition? So if I read this, we have, it looks like two situations. We have dry. We have when it's wet. What path is this car tracing out? A circle. That means that my net force is going to be Fc. What force is pushing this car in a circle? I'll give you a hint. It's just like the first question that we did in this lesson. When you're taking a corner, what force is pushing you in a circle? Friction. Friction is what times what? And Fc is MAC. By the way, which version of AC do you think circular acceleration, do you think they want us to use? V squared over R or 4 pi squared R over T squared? How'd you figure that out? They gave me a speed. Okay, so I'm going to go, this is going to be mv squared over R. Mu times, I don't know the normal force. Oh, but if I draw on the free body diagram, but I'm using the same one from back here, look, 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 look. I know another force the same size as the normal force. What? What do I need to find here in order to do the wet section? Yeah, you know what? I'm going to find what the coefficient of friction is in this equation. That's what the pavement is dry. And then for when it's wet, I'll divide that coefficient by 2 and use that to see how fast I can travel safely. So we're going to get a mu equals v squared over ger. (32 squared over 9.8, and what's the radius? 72? I get a coefficient of friction of 1.45. These must be really good tires. You can tell I made these numbers up. 1.451. Apparently, when it rains, we get half the traction. So when it rains, my coefficient of friction is 0.7256. What do they want me to find now? Maximum safe speed. We're moving in a circle, so I know my net force is centripetal. What's pushing me in a circle? Friction. It's going to be mu times the normal force equals m, and since they're talking about speed, I'll use v squared over r. I don't know the normal force. Oh, but look. I know another force the same size as the normal force. I think I can say mu mg equals mv squared over r. Yay, mass cancels. Oh, in fact, I get the same equation that we got way back in question number 1. I end up with v being mu ger square root. The square root of 0.7256, 9.8, 72. How fast can we take this corner at safely now? .6 meters per second. Oh. Where did my data go? 22.6 meters per second. Okay. A little technical comment on turning. The reason that when you turn, friction is inwards has to do with how our wheels work. When we turn our front wheels to turn the car wants to keep going in a straight line. And because it wants to keep going in a straight line, it exerts a force on the tires, and the tires exert a force against the road. The road then exerts a force back of friction. It's actually perpendicular to the tires, which is why it's towards the center of your circle. So the turning friction is actually static friction, since the wheel is not skidding, and static friction is not always opposite to motion like kinetic friction is. This is what you're doing when you're turning in a circle. We'll look at how we get artificial gravity next class. Pause hit, Mr. Dick. Pause here.